Hi, welcome back to this course on computational thermodynamics and kinetics of materials. Today we'll continue with thermodynamic assessment, essentially the input data for that. Let's see them. These are going to be the contents for today. Thermodynamic assessment input data. The thermochemical input data, we have seen quite a few of them in the last class. In this class, we will see about activity, how to get that using gas phase equilibrium methods and electromotive force measurement methods. And then we will see what different theoretical methods are used to get this thermochemical data. Okay, these are the two things we'll focus now. Gas phase equilibrium methods, electromotive force measurement methods. Let's see them. In gas phase equilibrium methods, we are going to measure the vapor pressure basically. Why? Because if you recall, activity is related to partial pressure. If you remember this, activity of A is equal to partial pressure of A, let's say on top of any particular phase, divided by partial pressure of A on top of pure A, which is the standard partial pressure of A. And we said this activity is related to partial molar Gibbs energy of A in this way. Ga bar phi minus Ga standard is equal to RT natural log of activity of A. I hope you remember that. So now if you want to measure this, there are a few methods. First one is static methods for measurement of vapor pressures. It is like this: vacuum is created in a container with a sample of interest. So sample is kept in a container and it is evacuated. Then equilibrium is allowed to be reached with the vapor given off by the sample at the temperature of interest. That's all. Then two options are available to measure the vapor that is coming out. One is equilibrium vapor pressure is directly measured using manometers, and then indirect optical methods are there where radiation absorption at characteristic wavelengths of the vapor species is used. Transmitted light through the vapor. This intensity indicates the vapor concentration, basically telling you the partial pressure and activity. Right. Now, the second type are called dynamic methods for measurement of vapor pressures. One technique in that is called Knudsen cell effusion spectrometer. It's a very special technique in which sample is placed in a Knudsen effusion cell, this kind of setup, and from there the sample's vapor atoms escape or effuse through a tiny orifice without collision. So that is important. This setup is something to do with the principle of the equipment, and the effused vapor enters a mass spectrometer where atoms are ionized here in the mass spectrometer, and then it is detected. The ions are separated by mass to charge ratio and detected. What kind of ions are they? Therefore, the ion intensity is proportional to vapor pressure of the species. Okay, this is how vapor pressure is obtained in this. I'm just giving a simple overview of this. Then there is isopastic method where two or more substance samples are placed in a closed container at the same temperature and their vapors are allowed to equilibrate. Okay, sample with higher vapor pressure condenses into the one with the lower vapor pressure until both reach the same vapor pressure. This is where isopastic condition comes, meaning the vapor pressures are same. Okay, and the change in concentration, mass or weight change, or eventually new compositions of the samples is measured, because this kind of exchange of matter happens and the composition of the initial samples will change. See, this kind of methods go on even for months. Okay, this kind of vapor pressure becoming equilibrated happens even over months. So that's the kind of time involved in this kind of techniques. From this, relative vapor pressure is obtained. Then we have this electromotive force measurement method. The electromotive force EMF generated by electrochemical cells can be used to measure partial Gibbs energies. It is like this. We have seen this equation before, and this part is equal to minus NFE, where the N is the charge, F is Faraday constant, and E is the EMF generated. And this is called as Nernst equation. We haven't seen this in the theory that we have seen for thermodynamics, because this is in a slightly different domain where electrical energy is used, the electric work is considered, and things like that. Through that, Nernst equation is developed and it is connected to the thermodynamic concept that we have seen, and this is how the electromotive force can be related to activity. So how to measure this? Electrochemical cells are used. They use either solid electrolytes or molten salt electrolytes. And in the electrolyte, we have electrodes. A working electrode, alloy or phase of our interest, is paired with the reference electrode of known chemical potential. So when this kind of setup is made, there will be an EMF generated and it is measured and used for activity measurement. So there is no partial pressure measurement here. Right. So what we have done is measuring the partial quantities. If you get the activity of A, you are going to get ultimately Gibbs energy, partial molar Gibbs energy of A from that, right? So when we talked about calorimetry in the previous class, we haven't talked about the partial properties there. But in this class, these techniques that we have seen now, vapor pressure measurement, EMF measurement techniques, all these give you partial pressure or all these give you partial molar properties. So how to get the partial quantities of the other element? Okay, let's say if it is a AB system, we got this G bar of A phi from activity of A. What about activity of B? Okay, this can be written like this: chemical potential of A. If you recall Gibbs-Duhem equation, there we said the chemical potentials are related like this. Okay, the chemical potential of A and B change when the overall composition changes, but the change in only one is independent. If mu A decreases, mu B increases accordingly, or vice versa. So that's what Gibbs-Duhem relation told us. Okay, we can use this relation and figure out the chemical potential or partial molar quantities of the other element. Using Gibbs-Duhem relation, the partial quantity of the other element in the system can be calculated. Now let's look at the common theoretical methods. When we say theoretical methods, the first one is methods based on quantum mechanics. When we say quantum mechanics, we call it first principle calculation. This term first principle calculation actually is a quite generic term. What it means is this: a philosophy that the prediction is to be based on a basic fundamental proposition or assumption that cannot be deduced from any other proposition or assumption, also known as ab initio calculation. Okay, so if this is confusing, I'm going to break it down for you. So what is fundamental proposition we are taking, and what are the other propositions we are ignoring when we do the first principle calculation? What is this fundamental proposition that is so powerful that without anything else, only this can give all the properties that we are trying to predict? Okay, these fundamental propositions come from quantum physics. You see, quantum physics is the most powerful fundamental science we have, and with that we can explain everything in the universe except the things that can be explained by theory of relativity. That's what is told, and we said in the very beginning of thermodynamics class itself that thermodynamics and even theory of evolution kind of things are equally fundamental, because the questions they answer are at an emergent level. Therefore, if you see the theory of knowledge, we cannot say as a hard and fast rule that this is the only theory which can give everything, answer to everything in the universe. So it's not such a theory, but it's extremely powerful in predicting so many things. Okay, so that's what quantum physics is. So quantum physics has these fundamental constants like Planck's constant, charge of an electron, mass of an electron, and so on. And these constants only will be used, and from that we can figure out any property. Okay, by using quantum physics, there are equations in quantum physics that tell you behavior of subatomic particles. You just take those equations, solve them to get the properties. Any other proposition, by that what we mean is relying on any empirical fitting parameters or experimental data. You don't need to correct what you get from quantum physics using these kind of things. Only quantum physics is good enough. That's why we call it first principle calculation or ab initio calculation. Right. Now to understand this, recall the internal energy that we have seen, especially the potential energy part of internal energy, where we considered an atom, and of course the atom has electrons fluffing around it, and inside that there is a nucleus, And this entire thing, we are going to treat it as this blue ball. And this blue ball, if we consider, we are going to say there is some kind of a electrostatic force field around that. And if we bring another atom with such a force field, both have this electrostatic force field, and if they come together at a particular distance, there is some kind of a potential energy, and potential energy gets minimized as they come to some kind of a sweet spot distance. So this causes a potential energy, and minimum potential energy state is the stable state. In quantum mechanics, this is what it is, and this is possibly a very crude picture of what is happening in this when we do quantum mechanics and solve Schrodinger wave equations and things like that. Basically what we get is this minimum potential energy where atoms will be stable. Okay, so let's see that in little more detail. So this minimum potential energy state, we said, is nothing but the chemical bond formation. Okay, we even plotted this potential energy versus distance curve. Two atoms quite far apart and the potential energy is 0, and as they come together the potential energy reaches a minimum value. They cannot go any closer than that point. Okay, this is how we got this potential energy curve. Now this minimum energy state is what we are interested in to get from quantum physics calculations. Okay, this minimum energy state is a force balanced state. Meaning, if you think about any forces acting on a material, if the material is stable, it means that all the forces acting on it are now balanced. If any one force is dominating, then the material will respond to the direction of that force, right? So if all forces are balanced, then we can say the material is stable. Similarly, if two atoms are in certain particular distance and they are stable, it means that all the forces, that electrostatic force field we are saying, so there are many forces. So if these forces are balanced, only then the material is in the, or this configuration of two atoms is in the minimum energy state or stable state. Okay. So our job is to figure out this force balanced state. What forces? Electrons interaction, electrons protons interaction, and protons interaction. Okay, we are putting electrons. You can imagine, even if you bring two atoms together, how many electrons are there? And if you bring a periodic crystal, then you can imagine how many electron to electron interactions are possible, electron to proton interactions are possible. It's going to get immensely complex. And how to calculate them? Schrodinger wave equation you have to use. Schrodinger wave function gives behavior of subatomic particles. So the behavior of an electron when another electron comes near that. Okay, so this can be calculated using Schrodinger wave function. Solve it to get the force balanced state. So there are so many electrons and protons, there is so much of forces acting between them. So solve Schrodinger wave equation, which gives the behavior of these different subatomic particles, how are they going to respond for different forces, and eventually when they will get to the state of balanced forces. Okay. Right. So this solve Schrodinger wave function is a quite complex job. It's computationally intensive for practical systems. Therefore, layers of assumptions are done to that, so that it is made usable in modern computational facilities. And these layers of assumption make quantum mechanics to density functional theory. So these are available in the form of codes. We can take these codes. So with all these assumptions, there are a lot of assumptions. With all of them, the code is going to run and give you some output, and you have to take it with a pinch of salt because there are a lot of assumptions involved. Quantum Espresso or WASP are the codes. This is an open source code. This is commercial one, Vienna ab initio simulation package. Any composition in any structure can be made virtually, and its total energy can be calculated. Okay, that's what these codes do. Any composition in any structure, imagine how powerful this sentence is. Okay, you can take a material and you can put it in a structure which is definitely not possible for it in nature, and you can get the energy of it virtually using these codes. Okay, DFT codes also can give different results depending on the input. Okay, this may be little confusing to you. What is input here? We are saying this is a composition, this is a structure, and we are asking these codes, give me the energy, let's say. And what are these different inputs we are talking about? Because for the same composition and same structure, we can set different inputs. If you go deeper into how these Schrodinger wave equations are solved, what kind of parameters are important for that, there are multiple things there. We are not going into the details of that, but depending on what kind of input is given, what kind of values are chosen for those different input parameters, we get different outputs, different values of this energy. Okay. And usually calculations are done at 0 Kelvin, and these calculated energies at 0 Kelvin are available in different repositories for numerous materials. Okay, these are few examples: Materials Project, NIST, Jarvis, OQMD, etc. And this is a website. This is a link to a tab in my website. Here I keep listing any new source that I come across, so you can refer that. Okay, so as I told, the subject is quite involved. There are separate courses and books available on this subject of density functional theory. If you are interested, you can go into that further. Right. So usually calculations are done at 0 Kelvin, we said, and these are 0 Kelvin total energies. What do we do with these total energies? Difference between product, let's say AB phase, and the parents, let's say A and B, total energy values give formation energy. It's more like the potential energy change part in the internal energy change. And this can be assumed to be equal to enthalpy of formation. It's more like what quasi-chemical theory does. It takes only potential energy change as the enthalpy change. So that kind of assumption can be used here as well. And there is something called convex hull construction that is used to understand the lowest energy structures. It looks like this. You see the energy is here and the composition is in the x-axis. And you can see there's some kind of a lowest energy hull kind of thing is drawn. This is convex hull, and this gives you for different compositions what kind of minimum energies we get. And you can see if for one composition there are multiple dots and the one here has the lowest energy. What are these different dots? This may be for the same composition. If you treat it in a different crystal structure, you get minimum energy in only one crystal structure, and that's going to be the stable structure in nature. So that is how it is treated, but you can already sense there is some problem. It is often not correct to derive thermodynamic conclusions only based on it, because this is just the enthalpy of formation or just the energy of formation. It's not even a PV term itself is not involved in this, and more importantly entropy is not involved in this. So only when delta H minus T delta S comes, we are happy, because that's where we can say we have minimum Gibbs energy. So this particular thing is not same as the lowest Gibbs energy envelope that we talk about when we talk about thermodynamic stabilities. So this is often done, this kind of mistake is often done even today. People figure out crystal structures of different compositions of many functional materials based on DFT, and only based on this they talk about whether the particular structure will be stable or not, whether certain dopant will be accommodated into a structure or not, things like that. But you can sense that the entropy part is missed. If it is missed, it's a bigger problem. If the configurational entropy is missed, it is still okay for many compounds because they may not have any chemical disorder. But when it comes to vibrational entropy, it can be quite significant. Okay, so vibrational entropy change cannot be ignored. In fact, it is not only the modern phenomena, it used to be more in the past. Few chemists avoided entropy. Nernst is also there in that. This group, arguably led by Van 't Hoff, believed in a simpler approach that was more accessible and appealing to the chemists, because the enthalpy change is quite significant in many molecules. So people think only that matters. Okay, the strength of their avoidance of entropy spoke most loudly in their silence on the subject, as best reflected in Van 't Hoff's massive and influential textbook in physical chemistry of 1898 to 1900, which contained not one word on entropy. You see, entropy is ignored in the past as well, but it is quite important to consider. At least the vibrational entropy should be considered. Okay. So now I'm going to introduce more terms. Don't be overwhelmed by this if you are new to this. Just get to know different names, different techniques. Okay, I'm giving you a very brief introduction, possibly the names and one or two sentences about that. So get to know these things. Okay. So we said 0 Kelvin temperature, 0 Kelvin energies we are getting. But what about the practical high temperature energies? Okay. For we call them finite temperatures. So for finite temperatures, we need to do something called Phonon calculations, and they will be taking care of the vibrational thermodynamics. Okay. Then for disordered solutions, there is something called special quasi-random structures. They can give different structures for disordered solutions that can be used for calculation. Then cluster expansion method is there, that is also based on quantum mechanics. And then EMTO, exact muffin tin orbitals, AIMD, ab initio molecular dynamics, and then DFT based Monte Carlo simulations. All of them are used to generate this thermochemical data. And semi-empirical approaches with DFT. Okay, there are some tight binding models, parameters fitted to band structures is more useful for chemical molecules rather than periodic materials. DFTB, density functional tight bonding, semi-empirical quantum chemistry methods. Okay, these are all used for getting the thermochemical data. Right. Then methods based on statistical mechanics, CVM, cluster variation method. It is used for calculating configurational entropy. And then even the Boltzmann equation itself, S equals K natural log of W, or the one that we have derived using the Stirling's approximation, all those formulas, basically they are coming from statistical mechanics. Okay, so these are again methods used to generate thermochemical data. And then methods based on classical mechanics and semi-empirical models. Classical MD, molecular dynamics, basically the molecular dynamics uses Newtonian mechanics. Okay, so that is one method that can give some thermochemical data. And then there is this model called Meidamus model. It's a semi-empirical macroscopic model. It is used for enthalpy of mixing, and it uses experimental values of elements such as electron density, size, atomic radius, things like that. And it is extremely quick. It's a small formula, and problem is it is very approximate. Okay, the calculated values are available for liquid state. That is basically one value for a system. Only liquid phase is considered, and it is given in this couple of references here. It is listed for almost all the binaries and some of the ternaries as well. You can refer to that if you want. Meidama enthalpy values in liquid state. But there is one problem in how it is used in the literature, used as enthalpy of the entire system. You see, we said here clearly it is available for liquid state. Okay, and it is used as the enthalpy for the entire system, especially in this high entropy Li literature. If you do that, uncertainty will be high because a system can have multiple phases. Okay, intermetallics, when people use this to figure out whether intermetallic will form or solid solution will form. So for that they use liquid state enthalpy of mixing, which can be quite misleading. Okay, so uncertainty will be high because system can have multiple phases with different composition and crystal structures, each with different enthalpy of formation or enthalpy of mixing values. So it can be quite different from one to the other. So one particular value for the entire system is in a way quite absurd. Right? So with this we'll stop. Thank you. I hope the lecture is useful. See you in the next class.